Okay, so today what we're going to do is introduce sampling theory. Sampling theory is concerned with finding the probability distribution of sample statistics. This is important because it will tell how the statistic behaves from sample to sample. Statistics are a good example of random variables. They depend on the outcome of a random experiment. The random experiment, the random phenomena, is the selection of the sample by some random means. So it's important to realize as you go from one sample to another sample, you'll have variability coming from the same population. It's important to be able to assess that variability, use it to assess the accuracy of decisions made from the samples. Sample is a subset of the population. You take a sample because it's probably too costly to take the data from the entire population. A statistic is a numerical quantity computed from the sample. Example, samples mean, sample standard deviation, sample proportion. A parameter is a numerical quantity associated with the population. Consider the parameter is fixed, can't change unless the population changes. But it's a fixed number. Observations on measurement X are X1, X2 up to Xn. These are random variables. They come from a population, and the population will determine their distribution. The observations are numerical quantities determined by the outcome of a random experiment. The random experiment is choosing the random sample from the population. The probability distribution of the observations is the population. That's where the data is coming. This is a smooth histogram of the variable X for the entire population. The population is unobserved unless you observed all observations in the population. Histogram computed from the observation. This gives you an estimate of the population. This estimate becomes more accurate the larger the sample you choose. The rectangular diagram becomes a smooth diagram. A statistic computed from the observations is also a random variable prior to the collection of the sample. It's a numerical quantity whose value is determined by the outcome of a random experiment. Again, the random experiment is choosing a sample population. The probability distribution of the statistic is called the sampling distribution of the statistic. This describes the random behavior of the statistic and will be used to assess how accurate the statistic is. It's important to determine the sampling distribution of the statistic. It'll describe its sampling behavior. And the sampling distribution will be used to assess the accuracy of the statistic when it's used for purpose of estimation or the purpose of hypothesis testing. Sampling theory is the area of mathematical statistics that's interested in determining the sampling distribution of various statistics. This is a mathematical problem. Many statistics end up having a normal distribution, a bell-shaped curve. This is quite often true of the population being sampled as normal, bell-shaped curve. It also is sometimes true when the sample size is reasonably large. There's a theorem called the central limit theorem, which says that statistics such as averages and means will have a normal distribution even if the population is not normal. combining random variables. These are the principles that allow us to determine what the sampling distribution is. So quite often we have more than 2 or more random variables and we combine them in a mathematical expression. Important question, what is the distribution of the new random variable constructed from X, Y, and Z by some mathematical expression? Example, suppose one performs 2 tasks independently. The time to perform task A comes from a normal distribution with mean 25, standard deviation 3. So that means that X will be a number coming around scattered about 25, and 3 will standard deviation will tell you roughly how scattered it is about 20. Y is the time to perform second task, B. It has a normal distribution with mean 15 minutes, standard deviation 2. Quite often we might be interested in the total time to perform the 2 tasks. So we construct from X and Y, T, which is just X plus Y. What is the distribution of T? If we can find that, we can answer the following question. What's the probability that 2 tasks take more than 45 minutes to perform? Another example, suppose you have a student who's taking 3 tests in the next 3 days. He's taking a mathematics test. X is the score he'll receive on this test. An English literature test. Y is the score he receives on that test. A social science test. Z is the score he receives on that test. Suppose, and this depends on the student, the mathematics test is coming from a normal distribution, mean 90, standard deviation 3. The test will depend on how hard it is, okay? The mean will depend on how good the student is in that subject. The English literature test has a normal distribution with mean 60, standard deviation 10. So that mark will come around 60. Spread will be determined by the standard deviation 10. And Z as a normal distribution mean 70, standard deviation 7. There's the distribution for which each X, Y, and Z comes from. Suppose we want an overall score. Score is going to weight the mathematics score by 0.5, the English literature score by 0.3, social science score by 0.20, and then we'll give it 10 bonus marks on top of the score. What is the distribution of the overall score? We know the distribution of X, Y, and Z. What's the distribution of the overall score? Quite often, the computation to compute from the random variables X, Y, and Z, we want to compute what's called a linear combination of X, Y, and Z. There we have numbers A, B, and C. We multiply X by A, Y by B, add those up, and then we add C. So some simple linear combinations, sum A is +1, B is +1. The difference, A is +1, B is -1. An average of the 3 values, 1/3 X plus 1/3 Y plus 1/3 Z, weighted averages. Here the constants that we multiply add up to 1, and some are larger than the others. Means of linear combinations. The mean of a linear combination, L, is computed the same way that L is computed from X, Y, and Z, except we replace X by its mean, Y by its mean, and so on. The mean of X plus Y is the mean of X plus the mean of Y. The mean of X minus Y is the mean of X minus the mean of Y. So the means are calculated from the means of the random variables in the same way the random variable is computed from the other random variables. The variances, this is a more difficult question. Suppose X and Y are independent random variables, then the variance of L, the linear combination, is A squared times the variance of X plus B squared times the variance of Y, and so on. C doesn't have any effect on them. Adding a constant will not have any effect on the variability. It'll just shift the value up at constant C, shift it down. It doesn't have any effect on how variable the quantity is. So the formula for the variance of a linear combination, L, is A squared times the variance of X plus B squared times the variance. So the variance of X plus Y, the variance of X plus the variance of Y. A is plus 1, B is plus 1. The variance of X minus Y, some people think it's the variance of X minus the variance of Y. No, it's the variance of X plus the variance of Y. A is plus 1, B is minus 1, A squared is plus 1, B squared is plus 1. Constant C has no effect on the variance. So let's take an example. We have X the time to perform task A, Y the time to perform task B. Both are normal, coming from a bell-shaped curve. The mean for X is 25, the standard deviation 3. The mean for Y is 15, the standard deviation is 2. Suppose we are interested in combining those two by adding them up. That will come from a normal distribution with mean. The means will be just added up, 25 plus 15. This is logical. It takes an average of 25 minutes to perform the first task, an average of 15 minutes to perform the second task. To perform the two tasks, it would be the sum of those two. This is computing the standard deviation. Standard deviation is just the square root of the variance. The variance of X plus Y would be plus 1 squared times 3 squared plus 1 squared times 2 squared, 3.6. So now that we've found out the mean and the standard deviation, we can compute the probability. Say the probability the task takes more than 45 minutes. See, the mean for the task would be 40. Now we want to see if it takes longer than 45 minutes. Again, you would compute the standard score of 45 minus 40 over 3.6, Z greater than 1.39. That can be looked up in the table, it's 0.082. In the second example, we have students going to be taking 3 tests. The scores on those tests are random variables. They'll depend on random quantities, how hard the test is, and so on. X is coming from a normal distribution with mean 90, standard deviation 3. Y is coming from a normal distribution, mean 60, standard deviation 10. Z is coming from a normal distribution, mean 70, standard deviation 7. We're going to compute an overall score by weighting mathematics with 0.5, English literature with 0.3, social science with 0.2, and then we're going to add 10 bonus marks. There's the distribution for the individual tests. value of x will be coming from underneath its bell-shaped curve. The value of y will be coming up from under its bell-shaped curve. The value of z will be coming under its bell-shaped curve. Now we want to know what the distribution of y of s is. This will have a normal distribution. The mean will be calculated from the means of x, y, and z in the same way that s is calculated from x, y, and z. Mean works out to be 87. That's high because we're giving the math score a higher weight. It'll have the 90 will have a bigger influence on, and plus we're adding 10 to the score. The next will tell us its distribution. Its standard deviation will be the square root of a squared times sigma x squared, b squared times sigma y squared, c squared times sigma z squared. All of those values are known. Putting them in, the mean turns out to be 3.635. So there's the distribution of x. It's a normal distribution with a mean of 87, a standard deviation of 3.63. Sampling theory. Here we're now interested in finding the distribution of samples. Again, just a quick review. Linear combination of a set of random variables multiplies each random variable by a constant and possibly adds a constant. There are the common random variables. The mean, you compute the mean of a linear combination in the same way you compute the linear combination from x, y, and z. You just replace x by the mean of x, y by the mean of y, and so on. Variances. If the random variables are independent, the random variables are not independent, it's a much more complicated formula, which we won't go into, but if independent, this variance of L is a squared times the variance of x plus b squared times the variance of y, and so on. The c has no effect on the variance. Normality is preserved. If the individual random variables are normal, the linear combination is normal. There's the formula for its mean. There's the formula for its standard. So x plus y will have a mean of mu x plus mu y, standard deviation sigma x squared plus sigma y squared. X minus y will have a mean of x mu x minus mu y, standard deviation sigma x squared plus sigma y squared. The distribution of the sample mean is just a linear combination. So you have n independent random variables coming from the same normal distribution, mean, mu, standard deviation, sigma. What's the distribution of x bar? X bar is just a linear combination where the weights are all equal to 1 over. The mean of x bar, you compute it from the mean of x1, x2 up to xn. Those are all equal to 2. The weights are all 1 over n. So there'll be n values all equal to mu over n. When you add those up, they'll be equal to. Now the next one is giving the variance of x bar. We square each one of these weights, multiplied by the variance of each x values. They have the same variance, sigma squared. So we get n terms equal to sigma squared over n squared, sigma squared over n. So if these observations are coming from a normal distribution, mean mu, standard deviation sigma, the sample mean will come from a normal distribution, mu x bar equal to mu, the same mean as the population. The variance is smaller, it's sigma squared over n. Standard deviation of x bar is the square root of that, sigma over square root of it. So here's the population being sampled. These are the probability distribution of the individual observations. They come from a normal distribution with mean mu, standard deviation sigma. This is the distribution of x bar. It's coming from a normal distribution as well. Its standard deviation is sigma over the square root of it. That becomes smaller and smaller, and the distribution becomes more compact around mu as n increases. So just summarize. Sample mean is normal. The distribution of the sample mean has exactly the same mean as the population, mu. The distribution of the sample mean has a smaller standard deviation than the population. It's sigma over root n compared to n. So this is just telling that averaging tends to decrease variability. Here's an Excel file that illustrates. Now, can you see that file? The black dots are the individual observations. This is the population being sampled. It has a normal distribution with mean mu.
Excuse
Then,
me.
yeah.
I can't see the file. I can just see the PowerPoint slide.
Okay, so what I'll do is I'll stop sharing and then go back to sharing the screen. So now you can see it. This is an Excel file. I've generated observations at random from the normal distribution, black observation. The red observation is the mean of those observations. It's the center of gravity of those observations. Now, if you go to formulas, if I press this button here, it'll regenerate the black observations, and the mean is just the red dot is the average of those observations. Press it again, it'll do another sample. The black observations are coming from the population. The red one is calculated from those observations. It's the center of gravity. It's coming from the sampling distribution of the mean, which is also a normal distribution. It's centered at mu, but its standard deviation is smaller. It's sigma over root n. Now, if I change this to n equals 20, there's 20 observations being selected. The standard deviation is a bit smaller. It's sigma over 4 square root of 20. Gain, I press recalculate. We recalculate observations that come from that distribution, and the sample mean is the average. If I change this to n equal to 100, the standard deviation for x bar becomes sigma over square root 10. It's a lot more compact. There's 100 observations. Pressing the calculate now, it'll regenerate those observations. See, you get a few that are outside. The red dot is coming from underneath the sampling distribution of x bar. Example, suppose we're measuring cholesterol level of men aged 60 to 65. This measurement is known to have a normal distribution, mean 220, standard deviation 17. So that means the measurements of cholesterol for men aged 60 to 65, they'll be coming underneath a bell-shaped curve centered at 220, and the 17 is how spread out this is. Suppose we take 10 males aged 60 to 65, and so these are the 10 measurements of cholesterol for men, for the 10 individuals selected at random. We want to, suppose we don't know the mean, we want to estimate the mean by the sample mean, X bar. It'll vary randomly. Compute the probability, it should be around 220. Compute the probability, it's between 215 and 225. To do that, we have to find its sampling distribution. The probability distribution of X bar is normal with mean mu X bar equal to mu equal to 220, and sigma X bar equals sigma over square root of n, 17 over the square root of 10, 5.376. So then we can use that to calculate the probability is within 5 of 220. Standardize this, divide it by the standard deviation, the mean, subtract the mean of X bar, which is 220, divide by the standard deviation. That changes X bar into a standard normal random variable, and the limits become minus 9.3 to plus 0.93. That we can look up in the table, 64.8. So there's a 64.8% chance that X bar will be within 5 of 220. The central limit there says that if n is sufficiently large, the sample means of random variables from any population with a mean of mu, standard deviation of sigma, will be approximately normally distributed with a mean of mu, standard deviation sigma over. So even though the population might not have a bell-shaped distribution, if n is sufficiently large, and the rough rule of thumb is greater than 30, the distribution of X bar will still be normal with mean mu, standard deviation sigma. So here's what the original population looks like. It's not a bell-shaped curve, it's a positively skewed distribution. You can show by mathematics that the distribution of X bar for n equal to 2 looks like this. For n equal to 20, it looks like this. So you can see the hump is forming. For n equal to 3, it has the for n equal to 30, it has almost a normal distribution. So even though the population is quite different than being normal, you can always make the assumption that for large sample sizes, X bar should have come from a normal distribution. So the conclusion, the sampling distribution of the sample mean is normal. That will be true if the sample size is large, and a rough rule of thumb is greater than 30. When the population is assumed to be normal, the sampling distribution of the sample mean is normal no matter what the sample size is. So if the data is coming from a bell-shaped curve, for whatever sample size is, the sampling distribution of X bar is normal. Central limit theorem says even if the population is not normal, if the sample size is reasonably large, greater than 30, the distribution of X bar will be normal. Example, suppose we had a normal population mean 50 standard deviation 15. We choose a sample size 9 and select. Find the probability X bar is between 45 and 60. Probability X bar is less than or equal to 47.5. Because the original population was normal, even for a sample size of whatever the sample size, the distribution of X bar will be normal. Its mean will be equal to 50 standard deviation sigma over root n. So you can then go ahead and calculate the probability that X bar is between 45 and 60. That's the equivalent to Z being between -1 and 2. That we can look up in the tables. That works out to be 81.85. That's that shaded area. That's true for the normal distribution with mean 50, standard deviation 5. The other question was, what's the probability X bar is less than or equal to 47.5? When you standardize, 47.5 becomes -0.5, and that can be looked up in the table. The chance of that is 30.85%. Now, suppose that this example here, the random variable is the price of a hotel room in Toronto chosen at random. Now, likely the price of a hotel room is coming from a positively skewed distribution. Most hotel rooms have a small price, but there'd be a few hotel rooms that would have a very large price. So it's unlikely that if I chose a hotel room at random, found its price, that observation would be coming from a normal distribution, probably coming from a positively skewed distribution. So if we took a sample of 50 hotels, they should be coming from a normal distribution centered at mu here, 109. The standard deviation would be the standard deviation of the population divided by square root of n. So we could then calculate the probability that the average cost for the 50 hotel rooms was less than 105. Suppose we took sample 50 hotel rooms and the average price was $120 per. That's quite a bit higher than 109. Is this strong enough evidence to refute that claim that the average price is 109? The solution, the central limit theorem applies because the sample size is large, greater than 30, 50. So we can assume that X bar has approximately a normal distribution with a mean equal to the mean of the population, 109, standard deviation of the population divided by the square root of n, 2.83. So that allows us to answer questions 1 and 2. In question 1, we want to find the probability that X bar is less than 105. That works out to be 0.0793. In the second question, I'm asking whether the $120 is large enough to refute the claim that the average price was 109. So to do that, we'll calculate if the average cost was 109, the probability of getting a value that large or larger. We get that's equivalent to the probability Z is greater than 3.89. The chance of that is 0.0001, 1 in 10,000. So Since the probability of getting a value that large is so small, it probably means that the average cost was not 109. The claim that the average cost was 109 is likely wrong. It's possibly larger. So just a quick summary. The mean of the sampling distribution of X bar is equal to the mean of the original population. The standard deviation of X bar is also called the standard error of X bar, standard error of the mean. Sigma X bar is sigma over the square root of n. The distribution of X bar is exactly normal when the original population is normal. The central limit theorem says the distribution of X bar is approximately normal, regardless of the shape of the original distribution when the sample size is large enough. The sampling distribution of a sample proportion. So suppose P is the proportion in the population that has a certain characteristic. We take a sample of n observations from that population, and we count the number that have that characteristic. That's X. You can think of when you take a sample, each individual case is either a success or a failure is in the group which we're computing the proportion for, or it's not. Then the sampling distribution of P hat is approximately normal with mu P hat equal to P, sigma P hat equal to square root P 1 minus P. So this will tell us where sample proportion, it's random, will tell us the random behavior of the sample proportion. Recall, this is the logic behind this conclusion. Recall, X, the number of successes in n trials, will have a binomial distribution with parameters n and p. For n large, X has approximately a normal distribution. Mu equal to n times p, sigma equals square root n times p times q, square root n times p times 1 minus p. The sampling distribution is just 1 over n times x. So its distribution, its mean will be 1 over n times the mean of x, which is n times p. 1 over n times np is equal to p. Standard deviation of p hat is 1 over n times sigma. 1 over n square root n times p 1 minus p square root p 1 minus p. So the sampling distribution of p hat will be centered around p. This is useful if we're using p hat to estimate p. The standard deviation is square root p 1 minus p over n. Notice that the standard deviation gets smaller and smaller as you increase the value of n, so it becomes more and more compact around the value of p. Example, suppose 20% of voters favor candidate A. So we are going to have a poll with, we go out and we ask 600 voters who they favor. The proportion who favor candidate A will be coming from approximately a normal distribution with mu p hat equal to p 0.20, sigma p hat equals square root p 1 minus p over n, 0.20 times 0.80 times 600 divided by 600 square root 0.0163. There's the graph of the sampling distribution of G hat. We want to know how accurate a sample will be. What's the probability that p hat will be between 0.18 and 0.22. So that's within 2 percentage points of P. We know that P hat has a sampling distribution mean equal to 0.20, standard deviation 0.01633. So from that, we can calculate the probability P hat is between 0.18 and 0.22. Just standardize the limits. 0.18 to 0.22 become minus 1.225 to plus 1.225. That we can then look up in the table, and we see that with 77.94% chance that P hat will be between 0.18 and 0.22. Maybe at this point we'll stop and I'll answer any questions that you have. So are there any questions? If not, I'll end the lecture.
I have a question.
Sure.
So the part where you calculate the probability of Z being between two bounds, how do you calculate that?
Okay, you have the table for the standard normal distribution. It will give you the area from 0 up to the value. Let me just share with a screenshot. Okay, so these numbers here are coming from the table for the standard normal distribution. Escape. I'll just shut down this. And here I'll go to, well, okay, so here is stats 245. Here are tables. This is tables for the standard normal distribution. They give you the area from 0 up to a point. So if I want the area between 2 points, I look up the area that's below the upper point and subtract that the area that's below the lower point. So, yeah.
Okay.
So suppose the upper point was 1.2. Well, if I go down to here, I have to go to 1.2. The area below that is 0.9032. If there was extra, if it was 1.25, I'd have to go along to here. So that's the area that's below 1.2. But and suppose we wanted the area between minus 1.2 and plus that, I'd have to go up to here. And get minus 1.2, and that would be that. So that number I'd subtract from the other number.
All right, I see. Thank you.
Now you can also find those values using Excel. Here, I'll just use Excel. Pick up a blank workbook. Here I'll put 1.2. Here I'll put minus 1.2. And here I'll get equals norm S distribution. This is the value of Z. This will give me that tabled area. If I was going for the minus 1.2, it would be norm S. The S is the main standard normal. For this value here, it's minus that. That's what was in the table. And the difference would be the area in between.
So the difference in the area, is that the probability?
Yes, that's the probability of being between the two values.
Okay. Oh, because the area of the whole thing is 1?
The area of the whole thing is 1, and the thing that's in the tables is for different values of Z. I'll put, wait a second, no, I'll just, this minus this. That's the area in between those two values. This is Z. This is the probability that a random variable with a standard normal distribution is less than or equal to Z. Now, because quite often you don't have a computer, you might have to use the table. So if I drew a standard normal distribution, it's centered at 0, standard deviation 1. This is the area below minus 1.2. This is the area below 1.2.
So you're always calculating the area below whatever the value is?
Well, what's given in the table is always areas below, but sometimes you want to get areas between. So in that case, you have to look up the two values and subtract. And it's useful to draw a graph, okay, of the area that you want to calculate. The area that's in the table is the area below.
Okay. Oh yeah, just
Yeah.
one more question. What's going to be
Sure.
going on in the lab?
Okay, what I'm going to do is tell you how to do the second computer assignment. Okay,
Okay.
so
Yeah.
that's what I'll do in the lab.
All right.
Okay, so at this point we'll stop because I have to give another lecture